Hey everybody, Morgan here. So we're talking about the last couple of pages of the Unit 9 Kinetics outline for honors. And now we're going to be looking at the idea of reaction mechanisms. Now a reaction mechanism is the series of elementary steps by which a reactant is converted to a product. Good definition. Now, for a mechanism to be plausible, it must meet two restrictions. The equations must add up to give the overall balanced equation, and it must agree with experiment. If all those individual steps don't add up and give you the overall equation, it's just not right. And experiment can destroy any theory. So, what this is saying is that reactions don't always happen in just one step. For example, C2H2, which has a triple bond between the carbons, can react with water. The triple bond opens up to just a double bond, then an H and an OH from the water add on. Now that's not terribly stable, so immediately it converts over into this, where the carbon is double bonded to the oxygen, you have a single bonded hydrogen. So this would be the first step, and that would be the second step of the reaction mechanism. Okay, this guy in the middle here, it's called an intermediate. A species, neither reactant nor product, that is both produced and consumed in a reaction mechanism. Now, sometimes we might refer to those as a transition state. The difference is that a transition state is typically very high energy, and an intermediate doesn't necessarily have to be high energy. But you can use the terms almost interchangeably. Now, these individual steps are often referred to as an elementary step, which is a step whose rate law can be written by inspection, meaning the stoichiometry would actually tell us about it. Some people like to use a fancy term for that. They call it molecularity, which is the number of species that are colliding to produce the reaction in that step. And it's a pretty easy idea. Unimolecular means 1, bimolecular means 2, termolecular means 3. Okay, now if you have multiple steps in a chemical reaction, one of them is going to be known as the rate-determining step. And that would be the slowest step in the reaction mechanism. The reaction can't happen any faster than that step does. Okay, now, we've talked about the ice cream graph before, as we call it, but I want to look at it in a slightly different view today. First off, these all represent the same system. Same number of molecules, okay, speeds of molecules, total number of molecules is the same in each of A, B, and C. Now it turns out that A represents it at a lower temperature, B medium, C higher temperature. And what that means is, at a lower temperature, on average, particles are moving slower. And at a higher temperature, on average, particles are moving faster. So since the speed of the molecules matters for collisions and whether they produce a reaction or not, at a lower temperature, more of the particles will not have the necessary activation energy. Let's say I just draw a line here arbitrarily, right there. I say that that's how fast they have to be moving to actually produce a reaction. So, at the low temperature, almost all the molecules don't have that energy. But at the higher temperature, more than half of them do. So the reaction would be faster because they happen to have the activation energy responds to the colder temperature. Okay, that's the last 2 pages of the outline. Hope you're having a good day. This is Morgan, signing off.